Okay, this is video 9C. 9C and 9D are going to be concerned with truth tables. In this video, I'm going to explain what they are, and in the next video, I'm going to explain how to use them for different evaluations of sentences. So what's a truth table? Well, we can use truth tables to define validity, and so we can use them in completeness and soundness proofs, which I'm actually not going to talk about right now. They also provide us with a way to tell whether or not an argument is valid or invalid, so they're useful. But so what are they? Well, so here's the truth table for negation. So we have that if box is true, then not box is false. And if box is false, then not box is true. So the truth table for negation tells us when negations are true and when they're false. And it tells us when they're true and when they're false, depending upon the truth values just of the constituents. So what about for a conditional? Well, if the antecedent and consequent are true, the whole thing is true. If the antecedent is true and the consequent is false, the whole thing is false. If the antecedent is true and the consequent false, the whole thing is true. And if both antecedent and consequent are false, they're both false. I'll remind you that this is the natural language conditionals do not work like this. They're more complicated, and we're giving the arrow this relatively simple meaning, interpretation, because it's easier to work with. So what about the truth table for the conjunction? Well, if both conjuncts are true, it's true. Otherwise, it's false. What about for the disjunction? Well, if both disjuncts are true, it's true. And if either one but not the other disjunct is true, then it's true. If both disjuncts are false, then it's false. Biconditional. If both are true, it's true. If either are true, if one is true and the other is false, it's false. And if they're both false, then it's true. So here they all are. Hooray. Good. So one comment here is that this is a system that is sort of classically bivalent. What does that mean? Well, so it means we have two truth values. We have the truth value true and the truth value false. Each sentence letter has exactly one truth value. It's either true or false. It's not both true and false. And it's not, could it be neither true nor false? No. It's got exactly one truth value. So no sentence letter lacks truth value. Every sentence letter has at least one truth value. And no sentence letter has multiple truth values. And in fact, it's a consequence of our the truth tables that every sentence has exactly one truth value. It's sentence in the language chapter 2. Natural language is probably more complicated than this, but if you have a language in which each sentence has exactly one truth value, then it's a classically bivalent system. Bivalent meaning two truth values. Okay. Sentences in our language have an important feature called truth functionality. So what does that mean? Well, it means that there are two factors. You take any complex sentence in our logical language, and there are two factors that determine its truth value. First, the main connective, and secondly, the truth value of its immediate components. So all it cares about are the truth value of the immediate components and its main connective. It doesn't care about anything else. So we can say that the truth of the whole, the truth value of the whole, is a function of the truth value of the parts. There are lots of sentences in English that are not truth functional. So consider box because circle. I say, well, so he is thirsty because he did not drink. Or he did not drink because he is thirsty. Well, the first is true. The second, you can imagine lots of situations where one is true but the other is false. And in normal situations, if the first would be true and the second would be false. You could come up with situations where it's the other way. But normal situations where it's true that he's thirsty and it's true that he didn't drink, one is going to be true, but two is not going to be true. The reason for this is that because is not truth functional. Because cares about more than the truth values of the components. If because was truth functional, then 1 and 2 would always have the same truth values. Why? Well, because they have the same main connective. Because, and he is thirsty and he did not drink have the same truth values, whichever sentence you're looking at. So, if because were truth functional, then 1 and 2 would always have the same truth values. because the truth value of the whole thing will be determined by what was the main connective and the truth value of the components, and those would be the same for 1 and 2. But because 1 and 2 can have different truth values, we can see that because is not truth functional. So lots of language is not truth functional. So the fact that our language is truth functional is a very special little feature of it, and it's critical for our truth. It's a consequence of the truth tables, of the way we've defined what our complex sentences mean. We've said that's what those truth tables do. They say if you look at that whole big truth table for each operator thing, and you find any value in there, there are 2 components. Which row are you on? That tells you what the truth value of the components here is. And which column are you on? And that tells you that's about what the main connective is. So our chapter 2 language is truth functional. It means it's not can't say as much in it as you can in natural language. But for that very reason, it's easier to do the logic of. Okay, so remember this diagram from back to the beginning of chapter 1 when we were doing parsing. So we could imagine assigning truth values to the component sentence letters. And if we do, then we're going to get truth values for, say, if P then Q is going to be false because it has a true antecedent and a false consequent. And not P is also going to be false because it has the thing it's a negation of is true. And so the whole thing is going to be true because it's a conditional with a false antecedent. What this diagram is an example of is the fact that when you fix the truth values of the component sentence letters, you fix the truth value of any sentence you build up out of them. Right? Remember, if you think about what on the truth tables that we started with say, they just said, given the truth values of the immediate components, you get the truth value of the whole thing. But what we're showing here is that in fact, if that's how it works, it means that all that actually matters are the truth values of the sentence letters. Once you fix those, you fix the truth value of everything else. So if you were not sure about this, you could think, okay, first we fix the truth values of P and Q. That means we then, at stage 1, so that's stage 1. At stage 2, we observe that means that everything that has P and Q as its only immediate members, so it's built up of just its only components are P or Q and nothing bigger than P or Q. So not P, not Q, if P then Q, if Q then P, P and Q, Q or P, and so on, all those. Then you fix the truth values of all of those. But that means you've also fixed the truth values of all sentences built out of everything at the first 2 levels. And that means you've also fixed the truth value of everything built at the first 3 levels, and so on. In fact, you fix the truth value of every sentence whose ultimate sentence letters are just P and Q, or P or Q. So our method actually fixes the truth values of all sentences, what we've given. And so in the next video, we'll be talking about how to apply truth values to determine, or truth tables to determine whether or not a sentence is a tautology. But this property of truth functionality is what allows us to do that. We say if we fix the truth values of the sentence letters in a complex sentence, we fix the truth value of the whole. And it's because of this that our method is going to work for telling us whether or not a sentence is a tautology, which of course we'll have to find out what does that mean. So, okay, next video coming up.